Video 3 of Chapter 9, where we will continue on with our significance testing, but this time around for a difference in two proportions. More than 25% of the millions of Americans who travel to high elevations each year, often to hike, camp, or ski, will suffer from altitude sickness. Now, I don't know about you, but I've been to Rocky Mountain National Park in Colorado, and when I first went there, I felt absolutely miserable because of the altitude change. And so maybe you've suffered from altitude sickness as well. Now, in 2012, researchers at Stanford University School of Medicine found that ibuprofen significantly reduced the incidence of altitude sickness in a double-blind, placebo-controlled trial. And so this is a legit medical study that happened here. And if you want to use my link down there, you can actually read the full details of this medical study. Now, some background information. There were a total of 86 volunteers that were randomly assigned to one of two treatment groups. They all traveled together to higher and higher altitudes throughout the day. So they just didn't travel from point A to point B continuously throughout that day, but they stopped at various altitudes as they were traveling higher and higher and higher up. Now, 44 of those 86 volunteers were given 3 doses of ibuprofen, and 42 of those volunteers were given 3 doses of a placebo instead. One thing that's always kind of puzzled me is if you have 86 volunteers, why not just do 43 and 43? And why make it just slightly different? That just kind of bugs me. I don't know about you guys. Now, the null hypothesis in this medical study would assume that the proportion of participants who experience altitude sickness really should be the same, regardless of what medication was taken. And yes, I know placebo isn't real medication, but we needed those volunteers to think that they were actually taking medication. So the null hypothesis in this medical study was that the proportion of people who took ibuprofen and the proportion of people who took a placebo, that they would experience the same levels of altitude sickness. Now, we can write it as that these two proportions are the same as each other, but we could also express them as a difference. So if the proportions really are the same, like maybe this is 40% and 40%, or maybe it's 29% and 29%, but if they're the same equal proportions, then the difference of those proportions would be 0. So we could write our null hypothesis a slightly different way, as a difference in the proportions. And the null hypothesis in this scenario, assuming that we're saying that they are equal to each other, the difference would equal 0 specifically. Now, again, you may write it this way, or you may write the null hypothesis as a difference and tell me that the difference would be a 0 difference. The alternate hypothesis wants to show that the proportion of participants who experience altitude sickness would be less for those who took ibuprofen than a placebo. So we're focusing on the proportion of people who have less altitude sickness. So they're saying that the proportion of people who took the ibuprofen is actually going to be a smaller amount than the proportion of people who took the placebo. And again, we could write it as a simple comparison that the ibuprofen people is going to be less than the placebo people. But again, if we wanted to look at this as a difference, then we could subtract over the placebo proportion and say that the difference in those two proportions would be less than 0. So again, if you think about if ibuprofen was a smaller percentage and placebo was a larger percentage, then a smaller number minus a bigger number would be a negative value, right? A negative difference. And how can we mathematically talk about negative differences? Well, they would always be less than 0. Now, on the flip side, if we wanted to, some people are like, I don't really like talking about negative differences. I want to talk about positive differences. Well, you could just flip-flop around your two proportions. Instead of saying that the ibuprofen minus the placebo would give me negative differences or less than 0, we could flip the placebo up front and say, well, my placebo proportion minus my ibuprofen proportion, those would actually give me positive differences, or they would be greater than 0. So you can state it whichever way you prefer. It doesn't matter if we do ibuprofen minus a placebo or placebo minus ibuprofen. The only difference that we'll see, though, is in the sign here. One of these will be greater than 0 and the other one will be less than 0. Now, for our conditions, we will literally have to do everything twice. Do we have 2 random samples? Is the independent condition met twice for our 2 populations? And is the normal condition met for both of our sampling distributions, essentially? Now, the normal condition, I will tell you up front, is going to be a little different than what it was when we were just testing out one proportion for one sample. So again, for the random condition, you must be explicitly told that there are 2 random samples, or technically, we're going to have random assignment in this problem. Now, this is kind of a new part we hadn't mentioned before about random assignment being a possibility for the random condition. We had just said they have to say random sample or they have to say SRS. But in medical studies, you can't randomly choose people to be a part of medical studies. That's not how things properly work. And so we need to have volunteers come to our medical studies. Now, when we get these volunteers who are not randomly selected, we will need to really introduce some sort of randomization into that experiment. And so we will randomly assign them to whatever treatment that they will be a part of. And in this case, it'll be the ibuprofen or the placebo group. All right, next up is the independent condition that we would normally have to check twice in this situation. But there's a little information that I need to let you know that happens to apply to this special situation. If no random sample or samples are taken and volunteers are used instead, and random assignment is at least used, there is that aspect of randomization, but it's only for the random assignment of treatments or the random assignment of volunteers to the treatments, then technically you do not have to check the independent condition. So just to remind you, it said in the original problem that we had 86 total volunteers. So what are you supposed to write for the independent condition? Well, you can still go ahead and complete the independent condition. You can always check it. Even on the AP exam, if you're not supposed to check the independent condition, but you do it anyway, if you do it correctly, they will just kind of overlook it. And they'll go, well, you didn't have to do it, but you did it. And as long as you identify the population correctly and 10 times the sample size correctly, then we'll just basically overlook it. We'll say no harm, no foul in that situation. So option 1 is you can go ahead and check the independent condition. Or option 2 is you could just state out the sample was not random, so the independent condition is not necessary to check. Or really option 3 is just don't write anything. Just know in the back of your mind, if the sample was not random, then you don't have to check the independent condition and move on to the third and final condition. Now, here's where things get a little different for the normal condition. It's not just looking at n times p and n times 1 minus p, both being greater than or equal to 10. We actually have to make 2 changes. Number 1 change is we can't use P because we don't have a claimed population proportion for the ibuprofen users, and we don't have a claimed population proportion for the placebo users, right? We weren't claiming their individual values. What we were looking at is we were comparing them to each other. We were saying that they were equal or their difference was 0, or that their difference is going to be greater than, less than, or technically could be not equal to. So we don't have claimed population values to use. So we can't use P, we would have to use P hat. We'd have to use a sample proportion. But here's where the other change comes into play. Notice this says P sub C. And so what on earth is P sub C? And not only that, notice this P sub C is used in all 4 of these cases. The only difference we're really going to see is with the sample size. We have our first sample size and our first sample size times this P hat sub C. And then we're also going to do the same thing with our second sample size with the same P hat sub C. And then again, the sample size times 1 minus P hat sub C. So what is P hat sub C? Well, P hat sub C represents our combined sample proportions. why we are going to combine them together instead of thinking of them as separate things is because our null hypothesis was that the population proportions would be equal to each other, right? We're saying that they're going to be the same. And so if they're really the same, then we could use one or the other, but the next best thing to do is just to combine them as if they were just one great big sample. So out of all of the confidence interval and hypothesis testing we're going to do, this is the only time that this has a little difference to it. And so what we're going to do is we're going to add together all of our successes that we saw from our two different treatments, from our ibuprofen and our placebo, and we're going to divide that by the total sample size from our two groups. Now, a common misconception is that we were really taking our two sample proportions and we're just adding them together. And that's not mathematically true. The difference is very, very slight. I will say these two values are very close to each other, but they're not exactly the same mathematically. So again, we are going to combine all of our successes as the numerator. We're going to combine all of our two sample sizes as the total sample size for this p hat sub c. Now, of the 44 participants who took the ibuprofen, here's some information we need to know. That 19 suffered symptoms of altitude sickness, whereas 29 of the 42 placebo participants had symptoms. So our ibuprofen group, and really I should put p hat here for my ibuprofen and p hat for my placebo group. Ibuprofen sample proportion 19 out of 44. Sample proportion of my placebo people 29 out of 42. So in the end, if I were to combine together all of my ibuprofen and placebo successes, if you will, I get 48 in total here. And then if I combine together my two sample size groups into 86, and I take 48 divided by 86, then that gives me approximately 55.81%. So this is our p hat sub c number that we are going to use. So first sample size, this was our ibuprofen people, which was at a 44. I need to multiply that by 0.5581. I also need to take my 44 and multiply that times 1 minus 0.5581. And then for my ibuprofen group, I had my 42 people times the same 0.5581. And then my same 42 people times 1 minus 0.5581. Are all of these four values greater than or equal to 10? And so I can use my calculator. Let me grab my calculator. Let's do 44 times 0.5581. And I get that this first number here is 24.56 approximately, which would mean, what's my leftover here? 19.44? Is that right? I think that's right. 44 minus 24.56. Yeah, 19.44. So both of those are good, greater than or equal to 10. And then if I do the same thing for my 42 times 0.5581, then I get 23.44, which is greater than or equal to 10. And then really 42 minus my 23.44, how many theoretical failures would I see? 18.56. So notice all four of these are greater than or equal to 10. So overall, we are saying that the sampling distribution of the difference in the proportions is approximately normal. So this is going to allow us to use normal CDF later when we get to the calculation phase. So again, this is definitely the one thing that you have to practice a little bit with. But if you use your calculator command, when we get to the calculation part, it kind of reminds you that there's something weird and different going on here. So you could always come back to this condition and fix it up if you need to. So speaking of those calculations, remember that standardized test statistic formula that we had talked about previously in video 2 for one sample? Well, it doubles in size when we talk about two proportions here. Now, it literally looks just like the same thing we had before, right? We had z equals p hat minus p divided by, and then that standard error, p times 1 minus p over n. That was whenever we just had one proportion that we were wanting to hypothesize and test against. Well, now we're looking at the difference of our proportions. And so the difference in our proportions is going to come from our sample. And the parameter value here, the difference of our population proportions, is typically, I'd say most of the time, going to be that zero value. Like we were just saying, is there a difference between these two? And in the null hypothesis, if there's no difference, then we said that would be a zero difference. Now, are there times where the difference would be something other than zero? And it could. It could be something other than zero. But I would say most of the time, we're looking for a zero difference. Now, we're also going to use that 0.5581 number downstairs for the standard error. And notice we have to use that 4 times down there. Now, the one little difference is we do get to use the respective sample sizes down here. So down here, we would get to use 44 for N1 and 42 for N2. So if I were to crank this whole thing out here, my P1 hat minus P2 hat. P1 I'm defining as my ibuprofen group, P2 is my placebo group. So I had 19 out of 44 minus 29 out of 42. And then I'm subtracting the hypothesized difference. And again, remember, this is typically going to be 0. Do you really have to write minus 0 here? Mathematically, no, you don't. But I always like to see that you recognize that there should be a number here. That number just happens to be a 0 because that is the claimed value. And then once I divide by the crazy standard error formula, which again, you will be given on the formula sheet for the AP exam, so you don't have to worry about that crazy square root down there. Then I get a z-score, a test statistic of negative 2.414. So what we're saying is the difference that we see here is 2.414 standard deviations below the mean of when the two proportions would technically be equal to each other. So now, since that was a negative test statistic, then we're going to calculate the probability, our p-value probability, that we would find other test statistics that would be less than or equal to. And again, we say less than or equal to because that test statistic is negative. If it was a positive test statistic, wrong way. If we had switched around our proportions and we did placebo minus ibuprofen, we would have gotten a test statistic of positive 2.414. Then we would have said greater than or equal to positive 2.414. So we get to use our normal CDF command. Our lower bound in this situation is going to be negative infinity all the way up to the negative 2.414. So there's our lower bound, upper bound, and we still get to use the mean and standard deviation of 0 and 1. Now, putting that into our calculator, we get a p-value that comes out to be approximately 0.00788. How does that now compare to our significance level? Well, what was the significance level? I don't think they really stated it. Let me jump back real quick towards the beginning of the problem. What did we say? Did we say anything? Did they state anything? No, they never said what the alpha level is. Now, that brings us to a good point here. The alpha level, typically for medical studies, is going to be 1%. And the reason why it's typically lower than our typical 5% is because in medical studies, it may come down to a matter of life and death if medication is going to help or hurt patients. Now, in this particular study, just talking about altitude sickness, it's not that big of a deal. So we're just going to use our typical 0.05 significance level. Even at a 0.01 significance level, we're going to make the same decision. And that's that our p-value is smaller than a 5 or a 1% level. And so therefore, in the end, we are going to reject the null hypothesis. So now let's use our calculator. Now, the name of the procedure is a 2-sample z-test for a difference in proportions. Now, instead of saying a difference in proportions, you could write out P1 minus P2, because that's really what a difference in proportions represents. It's the population proportions, and it's a difference of those two. Now, we're going to be trying to find in our calculator the 2-prop z-test command, which again, if you hit stat, scroll over to tests, I believe this should be number 6 on your list. And when that pops up on your screen, we've got to put in some data. So x1 over n1, this represents really our first sample proportion. This is the ibuprofen data here. So 19 out of 44 people experienced less altitude sickness. And then x2, n2 represents our second sample proportion. And so 29 out of 42 experienced altitude sickness. Now, for the alternate hypothesis, this is where we've got P1. Remember, this is our ibuprofen group. How does that compare to our placebo group? Was the ibuprofen group just not equal to the placebo group? No. We were wanting our ibuprofen group to be less than. They would experience less altitude sickness than the placebo group. So select that middle option there. And again, you're going to put your cursor on that and then select enter so that it fully accepts that particular command there, and then scroll down and hit calculate. And again, we need to identify the test statistic and the p-value for this step. Now, here's what that looks like. Here is that good old test statistic, and here is that p-value. Now, everything else here really just represents the other values that we already knew about, but just written in a different way. So the P1 hat, that is our 19 out of 44, 42, I can't remember, what was it, 44, 19 out of 44. The 0.69, that is our 29 out of 42. And then that special combined P hat, it'll even give that to me, but it doesn't have P hat sub C like we talked about. Just know that this P hat with no subscript is really the combined one. And then again, it gives us our 2 sample sizes. So what I want you all to do is to tell me what is the concluding statement. Now, I do want you to initially tell me, are you going to reject or fail to reject the null hypothesis? But then based on that, write the proper conclusion statement that we do or do not have enough evidence at the yada, yada, yada to conclude blah, 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 blah. So I want you to do that for me, and we will discuss that tomorrow in class.